Welcome to Study Loop.
So, from the problem given figure, we can observe the pressure volume diagram, which shows thermodynamic processes, and we are asked to evaluate the heat flow for each of the process. Now, for every single one. So, we have four processes. We have process from A to B, we have process from B to C, we have process from A to D, and we have the process from D to C. We are also given the work done in the state ABC and in the state ADC. Also, we are given every single internal energy state for the point A, for the point B, for the point C, and for the point D. So, from the first law of thermodynamics for every part of this problem, now this problem is a singular problem, but it has parts where we have to evaluate every single process given on the figure. So we will use the first law of thermodynamics for every transition, for every process. So it will be that Q equals delta U plus W, and delta U equals U final minus U initial. So this will be used for every process. So here we're given, and we will start from the process A to B. Now, in this case, first we will evaluate, for every process, we will first evaluate the change in internal energy, and then we will evaluate the work done, or we will already have given the work done. So, and then we will simply add them together to evaluate the Q, the heat corresponding. So for A to B, first we need to find out the change in internal energy, which is going to be delta UAB, and this is equal UB minus UA. We are given this, and we are given this term, so this is 240 joules minus 150 joules, and this equals to 90 joules. Also, the work done from A to B is going to be 0, since there will be no change in the volume here. So the work done is 0, and we can therefore state that Q equals QAB actually equals delta UAB, and therefore QAB equals 90 joules. This is for this part of the process. This is for the first process given on the PV diagram. So for the next process, which is from B to C, the work is not 0, so we can start by evaluating the internal energy change corresponding to this process. So BC equals UC minus UB, and we are given in the problem the value for UC and for UB, so we can substitute it 680 joules minus 240 joules. So this equals to 440 joules. Now we need to also find the work done, and this work from B to C can always be expressed as the difference, the subtraction of the work ABC from the state ABC to the state AB. So ABC minus WAB, and this equals to, this will be 0, obviously, and this has a given value, so it will be 450 joules. minus 0, so it stays for 450 joules. Finally, the heat BC is going to be equal delta U BC plus W BC, which equals 450 joules plus 440 joules. And the final value is 890 joules, which is the corresponding heat for this part of the process. Now we have the third part of the process, or the process from D to C. And in the same manner, we will first evaluate the internal energy change, and then we will find the work done if there is any. So here, observing, we always look at the diagram and see if there are any changes in the volume. If there are any changes in the volume, then there is some work done for sure, and we have to see how we will find this work done. If there are no changes in the volume, so then there is no work done. In this case, we will first start from expressing and evaluating the internal energy change, which is UdC, which is equal to UC minus UD, substituting the known values. This is 680 joules minus 330 joules, and this equals 350 joules as well. Now, in this case, from the diagram, we can observe that the work done from D to C is equal to 0. So, finally, QdC, the heat, from the first law of thermodynamics, equals to internal energy change plus the work done, which is equal to just internal energy change, and substituting the obtained value, we have that the heat corresponding to this process is 350 joules, just this value. Now we have the fourth process, which is from A to D. This is the fourth. And we can see from the figure that we have some work done here, and this work, AD, can be evaluated from the work ADC minus work DC. So look at this. If here is the point A and here is the point D, the state of the work that we need, we must include A and D. So it will be A, D, but it also must include a third point. So this is the point C. And then from this state, we subtract the work at the state of just these 2 points, DC. The same algorithm is being applied in the previous evaluations of the work done. So substituting the values that are given in the problem for these work points, we can see that it is equal to 120 joules minus 0 joules, which is just 120 joules. Also, we need to find the internal energy change, which is U AD. We will just subtract UD minus UA, and this will be equal to 330 joules minus 150 joules, which equals 180 joules. So finally, the heat corresponding to this part of the process is QAD equals delta UAD plus WAD. And substituting the obtained values, we have that it is 120 joules plus 180 joules. And the final value is therefore 80 equals to 300 joules of energy in heat. We can see from the results that every heat, for every part of the process, for every 2 points, the heat Q is always positive. This implies that the whole process together will absorb the heat, and the whole system will absorb the heat. So the heat from the outside, from the surroundings, is going directly into the system and is being absorbed by the system, which is also the answer to the final question of this problem. I hope that you find this helpful, and I hope to see you in another lesson.